from Havanov homology, and we heard this already this morning, that Havanov homology is a categorification of the Jones polynomial of knots or rings. So the Jones polynomial is a Laurent polynomial P, which is associated to a Norda link, and categorifying means that you realize this as an Euler characteristic of a complex of Grothendieck vector spaces. So for instance, the easiest case is if you take an unknot, then you associate to this, so it has Jones polynomial Q plus Q inverse, you associate to this, or one of it is this vector space Cx modulo x squared, where you put x in degree 2, you shift everything by -1, then you have something in degree -1, a one-dimensional vector space, and a one-dimensional vector space in degree 1. So that means taking the Euler characteristic, or here just the Poincare polynomial is Q plus Q inverse. Okay? So the crucial thing here is for taking a Poincare polynomial and realizing in this way a polynomial is that your coefficients are natural numbers. They are dimensions of a vector space. So now, of course, you want to extend this to things living over the integers. And we had this already this morning. You can do this by taking a crossing, like this, and you resolve it in the Kaufmann bracket way, so which defines the polynomial then associated to something which is a crossing. So for instance, this would be your link here. Then you associate to this one the thing which we had before, Cx modulo x squared, shifted by -1. To this you associate the shifted by -1. And two copies of this. You have a natural map, which is multiplication. And if you shift this again by 1 in degree, this multiplication is degree resolving, and this is given by this Q. So this shift in 1 is this Q. And in this way, you have Euler characteristic of this minus this gives you your Jones polynomial. This coefficients not necessarily integers, and not necessarily positive numbers, but integers. So now I want to go on doing this for colored Jones. What does this mean? This means if we take our unknot, we can label it not only by the fundamental two-dimensional representation, V1 of SL2, like we had before for Havanov, but by an arbitrary UQ-SL2 module, Vn, or by a number n. And then the associated polynomial is just the quantum number n plus 1. So P is q to the n plus q to the n minus 2 plus q to the n minus 4 and so on, up to q to the minus n. So this is this quantum trace, which is associated to this unknot. And why is it a trace? So it's definition of a trace. We take a bound ring of field. Let's say this is in our setup ZQQ inverse. So this Vn is a modulo over this. You take Vn and Vn dual, and you have the natural map from your bound ring to here. Let's say defined via this cup. Then what you want is you want to get this unknot, which means you take here the identity and you close it by taking the trace. This means here I take the identity corresponding to this one strand, enter the identity on here, and then I close it by going back to my goal. And if you calculate this in this specific case, you get that 1 is sent to this quantum number n plus 1. Okay, so this is the ordinary trace in monoid categories, as for instance defined in this paper of Scholz and Teichler. But what I claim is in this definition there are somehow hidden rational numbers. Of course, we would say no, because so far everything is defined over the integers. But you see these hidden rational numbers if you calculate this which means I take n cups, all labeled by the V1, the original Kovanov picture. Then I would, so this would be, I start from ZQ inverse. Then I go to V1 tensor n, tensor V1 tensor n, or its dual, which I want to identify. Then these pictures here mean I project to Vn. So let me do this like this. This would be projection, tensor projection, from this n-fold tensor product going to Vn, and they're corresponding for the dual. And then I do this trace map. And going back means I include this. And then so what does this picture tell you? This is just a simple linear algebra. It says if you want to compute the trace of, I should start here, the trace of a subspace inside a bigger space, you can do this by restricting the trace of the bigger invariants. So what they do is they associate to colored tetrahedron function, QQ. So here's my tetrahedron. And what they do is they color the edges of the tetrahedron by these irreducible representations, these VIs or VLs, which we had before. And then they draw this tetrahedron in this graphical network way. So these boxes here, which are 6 boxes, and they should all be labeled by a number. So 2 of them, there's the number missing. They correspond to the edges of the tetrahedron. And these parts with the red crosses, they correspond to the 4 triangles. Yeah? So now we can read this network from bottom to top, and it's a composition of things like this, or this projector, which is in my old notation over there, this projection from V1 to Vn, or inclusion n. So that means reading from bottom to top gives you a map which goes from ZQQ inverse over tensor product of several representations back to ZQQ inverse. Yeah? You can take one inside ZQQ inverse, and you can see what you get at the end, and this is your polynomial which they associate to tetrahedron. And in general, it's not defined over the integers. So what else can you do? You can also associate something to the sides, which is so-called theta network, which looks like this. So this depends on 3 sides. So these boxes again represent your edges of a triangle, and this network here is a morphism from ZQQ inverse to ZQQ inverse, and one is mapped to polynomial over Q associated to this network. And here I wrote down the explicit formula depending on the sides I, J, and K. And again, you can see it's not defined over the integers. So what else? So the second subset is the so-called 3-chain symbols, which tells you something about decomposition of tensor products. So you have the classical Clebsch-Gordan formula, which says if I tensor Vi and Vj, 2 representations for SL2, then it decomposes in an easier. But now you can ask the question, can we refine this decomposition by writing down explicitly these maps, these projection maps, and look at the entries in the matrices, the matrix entries, if I choose a certain basis. So I look at this to be j. So what would this be in this terms of diagrams? Vi tensor Vj to Vk. This in diagrams is, I start with Vi, then I go to V1 tensor I via the inclusion and to V1 tensor J via the inclusion. So this is symbolized by this thing. And I want to end up in Vk. So I go to V1 tensor K by putting lines like this. So there's a unique way to do this. And afterwards I project to Vk. Okay, so this is my projector. So when I ask the question, if I put here a certain basis vector and pair it with a certain basis vector here, what is the number associated? So if you bend this a little bit, you would get this picture. So this picture represents a number, which is this Vj symbol, which means take your F1 associated to this diagram and pair it with a scalar product with a certain basis. And again, this number is not defined over here. And the question is now, can we categorify these numbers? In particular, can we mimic or can we categorify Thoralf Biron, for instance? So this is the problem. So in fact, maybe I first should state a theorem, which I obtained in joint work with Frankel and Susan, building on earlier work with Ovanov and Frankel, where we realized all these tensor products of these quantum SL2 modules as a Grothendieck group of a category. So we categorified really these tensor products, and then intertwiners, so in particular these projections and inclusions, become exact hunters. And also, you can see the action of SL2 via exact hunters commuting these intertwiners. So we really lift the SL2 representation theory on a categorical level, so that if you go to the Grothendieck group, you get the original picture. But now, having written down all these maps here and saying that they are not really defined over the integers, I have to explain why we can do this on the level of the Grothendieck group at all. So what does it mean that we get something induced on the Grothendieck group coming from functors, which is not defined over the integers? And at that point, when I explained the ego factor this, he said, okay, I think I have to stop working with you because you can only work integral things, categorify integral things, and if there's something not integral, you should renormalize it. And so this was the starting point, but the end of the story is that we really have an interpretation of these special numbers in terms of Euler characters. So this is what I want to explain now. I want to start with a basic, almost trivial example. How should we interpret 1 divided by 1 plus q squared in terms of an Euler characteristic of something? So I start with my favorite algebra, which Ovanov tells us we should take, Cx modulo x squared, viewed as a graded algebra with x as before in degree 2, and I look at finite dimensional graded modules over this algebra. So A is the category, a B-name category of graded finite dimensional modules over this algebra. So now I pass to the Grothendieck group, and in the Grothendieck group I can write my algebra as 2 copies of the one-dimensional trivial module, once shifted, or once concentrated in degree 0, and once shifted up by 2 concentrated in degree 2. So this is because I have the short exact sequence saying that R is an extension of the trivial module with itself and with some gradient shift. So in other words, you can say R is 1 plus q squared times C in the group. Of course, clearly you can now invert this and say C is 1 divided by 1 plus q squared times R. The only problem is that this doesn't make sense in the Grothendieck group because, of course, C is giving you a basis over Z2Q inverse and R not. And I mean, it's not something reasonable. But what I claim is that this equation makes sense in a q-adic completion of this Grothendieck group. So you can write this 1 plus q squared formally as an infinite sum, 1 minus q squared plus q to the 4 and so on, and just view this as something which lives in the completion of the Grothendieck. What does it mean categorically? Categorically, it means that if I take my trivial one-dimensional module C, I can resolve it using R by this infinite resolution. So it's just repeating all the time with R. The maps are always multiplication with X, and this gives you your projective resolution. Yeah? So that means I want to say that this formal infinite series is categorified by an infinite resolution. Okay? And what happens if we compute the Euler characteristic? If I compute the Euler characteristic of the X algebra of this triple modulus itself, so it's defined as arithmetic sum of the dimensions of this graded X, then I get precisely 1 divided by 1 plus q squared. And this is probably come up in, say, geometry, like if you work with coherent or constructor machines, you usually would restrict to cases where you have at least only finitely many non-vanishing homologies.
May I ask why you get minus sign on the previous page?
Say again?
Where the signs come from?
So the signs come just from at which degree do you take your homology and have the alternative. So degree 0, 1, so 0 and 2 would give you plus, and 1 and 3 would give you minus. Now I take the graded Euler characteristic.
So you d squared is 7 degree 1.
So even so you have the homology degree, and and this is sigma 2 graded. Yeah? Okay. So in this, we get categories which are not so common in general in, say, geometric examples. And even worse thing is, coming back to our result which I stated before, we want to realize our vector spaces as Grothendieck group of something, but if I go to the unbounded derived category of some abelian category, then the Grothendieck group vanishes. So it becomes 0. This is a quite easy argument to see this. So that means somehow I have to change something. I want to work with infinite complexes to make sense out of these Euler characteristics, but on the other hand, I want to preserve my Grothendieck. And the idea is that we want to do something in between. So I want to not work with the bounded derived category, and I also don't want to work with the D minus. I want to work with the subcategory, which is squeezed in between these two, which is motivated by the Niels mixed Hodge structures. So what is this? So let me first explain you the solution, and then explain you the words which come in this theorem. So what I claim is that we can realize these Grothendieck groups which we need as a Grothendieck group of this smaller subcategory inside unbounded complexes. And the setup is as follows, so that A be a Noetherian Artinian abelian category, like the one which we had, modules over our ring R. It's mixed, so this is something like graded. I will give the definition afterwards. And then you have things like is enough projectives, and an additional thing which I want to call a tail twist, or which is called a tail twist. So let me abbreviate this thing by NAMA for Noetherian Artinian mixed abelian category, and then in enough projectives, so it's P, and a tape is T. So, and now I have this situation where we have our abelian category A, we have unbounded complexes, D minus A, and I have this category which I haven't defined yet, in squeezed in between. And then the statement is, if I look at the Grothendieck group of this, then it's, first of all, a module over set Q inverse. So the Q comes from a grading shift. And then the statement is that it's complete. So, and the natural map, which goes from my abelian original category A into this unbounded complexes category, which I have there, is injective, and it induces an isomorphism from the completed Grothendieck group to the Grothendieck group of this subcategory. So in particular, my formulas which I had before, like 1 divided 1 plus 2 squared, this makes sense in this completion. So that means in this Grothendieck group of this yet to define category, it makes sense to have such expressions.
I have a quick question. What is it?
So I will define what it is, but at the moment just think about it. A is a category of modules, finite dimension over graded grid. Yeah? And the take list will be then shifting of the grid. Yeah? But I will define it afterwards. Let me first state what we get out of it, so that you get an idea of why we should do it. Yeah? So this first statement says, the Grothendieck group of this category is naturally a module over this completion, Q are the completion of set Q inverse, and it's isomorphic to the completion of the K0 of my original abelian. Yeah? So the second statement is that if I take an object in my category, then it has a projective resolution with nice properties. And these nice properties are just a technical statement for saying the corresponding power series in this completion is convergent, and I have expressions of the form I would like. So just this formal thing which I did before, writing R as 1 plus 2 squared of the class of C, I wanted to write that C is 1 divided by 1 plus 2 squared R. So this point here says that this is possible. So you can just calculate in this Grothendieck group in the way how you think one should calculate. Yeah? So then if I take irreducible modules, simple modules, so in our case it would be just this C, or I take projective modules, in our case this would be R, and this little zero just says I should take it in degree 0. Then they span 3 submodules of this Grothendieck group over my completed ring, and in case of finite, which is the case in this example, they form 2 bases. So that means you have the span on the one hand side of this object and the span of this object, and they form both bases. So and then if you have another of these Namak PTs, and you have a right exact functor going from the original one into this one with some properties again, then it induces really a map on this completed Grothendieck group. So that means it is in the way how you would like to have it. So in particular, if I can realize these projections which appear here, going from there to there, as functors which satisfy these conditions from the last point, I get induced maps on these Grothendieck groups, and it's hopefully categorized precisely these focus which I wrote down before. So So in this way, we could make sense out of this 1/2, which I had in the previous form. So now, of course, I should tell you a little bit what is this mixed abelian category. And in fact, it's something quite easy and natural. So let's say A is a Euclidean in the abelian category. So something like modules, finite dimension modules over some ring. And it's called mixed in the sense of division if we have the following. If there is a weight function, which is a function which associates to each irreducible module or irreducible object in my category integer number. So for instance, if you have graded modules of a ring, you can just hope that every irreducible module is concentrated in a single degree, like we had in this example from above. Then you can just associate the corresponding degree. And we have this property that two simple modules only extend if the degree of the first one is bigger than the degree of the second one. Yeah? So that means if you think in terms of a module written down in a Jordan-Bell series, then you have at the top you have the big weights, and if you go down, your weights become smaller and smaller. Yeah? So what is a tail twist? A tail twist is just an auto-equivalence from A to A, such that if I twist a simple object using this tail twist, then the weight decreases by 1. Yeah? And of course, the standard example is the following. So take a positively graded finite dimensional algebra of complex numbers. So for instance, a cohomology ring of some complex projective algebraic variety. So I want to have a semi-simple in degree 0. And then you just say what is the weight of a simple object. It's just minus the degree of where the simple object is concentrated in. And then your tail twist is just shifting the degree down by 1. So unfortunately, everything is opposite to, in algebra, to geometry, but I think this is a standard problem, which you also have in shifts in divided categories, for instance. So that means our standard example of a mixed abelian, with all these conditions, category is such a category of modules over graded algebra. And actually, you can show that up to taking maybe projective limits, these are the only examples of such categories. So now here's the definition of this category which I want to work in. So I want to look at only complexes in my unbounded derived category, such that for each integer, only finitely many of these cohomologies have composition factors of weight bigger than n, and this is for all n in fact. So in other words, if you would take this object in this category and you would resolve it projectively, then you get an Euler characteristic which makes sense in this way. So this is precisely somehow written down the condition that this Euler characteristic makes sense. And so it's a very, I think, simple definition, but the theorem before tells you that all the constructions which you want to do really work. So and then if I go back, to this theorem which we had before, you should really replace this case 0 here by this completed Grothendieck group, and on the right hand side you have these categories of unbounded complexes which I just. Yeah? And then the statement is that all intertwiners, also including these projectors and inclusions, can be realized as exact functors, which when you go to K0, or to this completed Grothendieck group, So to give you an idea how this categorification works, I want to explain for you V1 tensor V1 in a little bit of detail. So first of all, I want to give you a geometric description. So what I claim is if I have V1 tensor V1, then I can write down the basis of this. So if V0 and V0 and V1 is the basis of this two-dimensional representation, then this thing is four-dimensional. This basis. Okay? So, and this categorification always works. If I take the weight spaces like this, then for each weight space I get a category. So in this easiest example, I would take here Riemannians of zero spaces in a two-dimensional space. Here Riemannians P1, and here two-dimensional vector spaces in C2. And what you can do is you can look at Hilbert sheets on this here as well, and here as well, and you just sum these categories. And this is an abelian category which has naturally a mixed hot structure and has this structure which we had before. But to make explicit calculations, in particular to explain you these projectors, I should rewrite this in terms of something which is easier to handle, and this is for me Lie theory, because here some of the projections I cannot really explain. So let me explain how I translate this into Lie theory. So these are equivalent categories, equivalent to these categories, and correspond to representations of GL2. So what I do is I interpret these couples here, 0, 0, 1, 0, 0, 1, and 1, 1, as weights for GL2C. So you have GL2C, and inside there I have the standard Lie algebra corresponding to the torus, given by diagonal matrices, and the weight is nothing else than a function from here to complex numbers. So that means I can realize this 0, 0, and so on as these functions. Okay? So let's say I have lambda, I call this h, I have lambda such a weight. Okay? So then I can look at the most natural module, which I can build from such a weight. This is called a Verma module. So you take this weight, which defines you a one-dimensional representation of this Lie algebra just by acting. So if you take something in H, you act on a basis vector of C just by this scalar, which you have given by this choice of this weight. Then you extend it to upper triangle matrices, so let me call this B, just by 0, and you into that. To GL2. So this is what is called a Verma module. So that means what corresponding to each of these basis vectors, you have precisely one of these modules. So now I have, for instance, this intertwiner, which is this cup, which when you calculate it explicitly in this basis here, gives you this value V1 tensor V0 minus Q V0 tensor V1. Okay, what does this mean in this language? In this language, this means I take this guy minus Q times this guy. module look like. And if you want to construct finite dimensional modules, you would take such a module and take it quotient by the maximal submodule, which looks in this case like that. And it turns out that it's precisely M01. So what this formula just tells you, take the big module, subtract the smaller module, but both are infinite dimensional, and what you get is the trivial module. Okay? So, taking the big guy, factor out the sub-Lohmer module, gives you only this one-dimensional trivial module. Yeah? So what I want to say by this is the value of this cup is this trivial module. Okay? So that means what's written here. So that means now we can ask the question, what should we associate to this unknown? So this unknown, of course, we should take this cup and pair it with itself. And what does pairing mean? Pairing means in this language, take the x delta of this trivial module L, so which is this one, which L is equal to L10. And if you compute this in this category where this Lohmer's left, in this highest rate category O, you get precisely Hovanov's algebra vector. So which means this guy corresponds to an object, a simple object, and pairing with itself corresponds to a vector space, which is even an algebra. Okay? So now I want to say, what does it mean to pass from V1 tensor V1 to V2? This is given by taking this category, which I told you categorifies V1 tensor V1, and factor out the CR subcategory, a Boolean category, and then you get something which categorifies C2, V2. So in this case, what you would get is here, so this is the same as in the category, you would get just gradient vector spaces. Here you would get gradient vector spaces. And then in the middle, you get modules of that. So this is a quotient category of this thing. And as you see, suddenly you are in the world that we have these infinite complexes. So in these categories, exactly this construction was used by Chuang and Wauquiez to give you a categorification of this irreducible SL2 modules, like this V2. So, and the point is, factoring out CR subcategories gives you a way to pass from things which have finite global dimension like this to things which have infinite global dimension, where you suddenly have naturally appearing these infinite complexes. Okay, so now I should explain you what is now roughly a categorification of this unknown. So here you see the picture of this network, which is the uncategorified version of a colored unknown, where I color by Bn, and the question is, what does it mean categorified? So let me explain this step by step. So then, what we do is we have to do this projection, which means we go from an abelian category to a quotient category. Okay? And what this picture at the beginning represents is a cube which resolves a simple object in here, like we had before. So before we said this thing corresponds to a simple object, and in general it corresponds to a more complicated simple object, and taking this quotient maps it to a simple object in a quotient table. And here you should think of that this is roughly like modules over rings, which look like homology rings of this sort of flat lattice we had before. So then closing up, like this, just corresponds to taking x in this quotient vector. So this is what this is the value of the carbon anode. So if you calculate this in this particular example, I have to take this cube, I have to take this projection, and then I have to compute the x with itself. And what I wrote down is, in these lines below, what you get as a contribution in each degree. And you see, these contributions are naturally quotients. So it's not an integer, but you get rational numbers coming up. But if you sum them up, just by mysterious accident, you get an integral number. But this is, I think, really just by accident, that for the I0 you get an integral number, but it should be really a rational number which you should get out of. And the point is, this algebra then categorifies this corresponding Euler characteristics, this number which you want to assign for the I0. So it categorifies colored Jones, but this is an infinite dimensional. And of course, you would expect, coming from the TQFT construction, that corresponding to an I0, you should have finite dimensional Frobenius algebra. Yeah? But categorified, I claim it's possible to have infinite dimensional algebras appearing, and nevertheless, you can still check this sort of identity move in this case. So it really gives. I did this with Schwarz-Susan. We checked that in this way you can categorify the colored Jones polynomial. Yeah? But somehow it's a little bit fake, this infinite dimensionality, because you just wrote 1 divided by 2, say as an infinite complex. If you would allow rational numbers, then this is not, I mean, it's still the same basis vector. It's just somehow including some scalars which are not defined over the integers, but which are defined over Q. So that means the usual argument for this, that the Frobenius algebra has to be finite dimensional, you have to adapt this to this situation, and then it still works. So what I claim is that you get a new sort of TQFT associated with much more complicated algebra. So and then let me finish with connections to other blocks. So these categorifications of these projectors indicated in these pictures, there was also done by Cooper and Pushkal using really the original Povanov art algebra, and they also have these infinite complexes, and we could actually show explicitly for n equals to 2 that our construction and their construction is more or less the same, and more or less means up to some derived Koszul equivalence. And by abstract nonsense, which characterizes these projectors, they are also the same in general for all n, but it's almost impossible to compute this explicitly. And somehow the advantage of their approach is that one can write down things more explicit than in our case, but on the other hand, in our setup, we really categorify the whole tensor product structure or tensor category of UQ as a two version. And of course, everything generalizes to SLK, except that you cannot draw these nice pictures, which are really special for Jones or SL2. Parts of it at least generalize to categorifications for modules of arbitrary real algebras, and this was done by Ben Webster. We will also talk about this. Then there is also known connections to Owadov-Rosansky theory. So they defined categorified non-invariants using matrix factorizations. And this was actually recently done by a student of mine, Hanno Becker, who constructed an explicit functor going from this world to the other world. Also, it's still not completely clear how the categories relate. So there is a functor, but we don't claim that there is a sort of equivalence of categories. And finally, I should say something about this retracing as I mentioned before, which refine this quite easy Gaussian formulas. So this was this entries in the matrix for this projections from a tensor product of two web stations to one web station, and they can also be realized in terms of an Euler characteristic of two modules. In this case, the modules are different, so it's not an algebra, but at least a gradient vector space. But the modules you put in are much more complicated than these sort of modules which we have here. They are so-called Arich-Chandra modules, and they appear from representation theory of real algebras. So, and for this point of view, it's really a new result in representation theory, whereas somehow what I used here is, for instance, classical Lie theory, which says that a triple module has a so-called Bernstein-Gelfand resolution in terms of Welmer modules. So this is really classical Lie theory, which I just used. But in these 3J symbols, you get new results in Lie theory by saying you can now compute at least the Euler characteristic of this X algebra. So nothing was known about this X algebra. And of course, using this sort of Kaufman network diagram combinatorics, it's very easy to calculate these numbers. And so at least we get some sort of